So the last time we met, we looked at diffraction, and if I may ask, we looked at diffraction of light, and we were able to say that diffraction of light deals with the change in the direction of light. And what causes the change in the direction of light? We say that there are mainly two factors that cause that change in the direction. We went on and looked at different examples, and we were able to derive the Snell's law, but also how to apply it. And in today's lesson, we are going to start looking at what we call the real and apparent depth. This is going to be our major area of concern. Now, what does it mean? When we talk about real and apparent depth, one you need to remember is that real, when you look at our pencil, when you look at the pencil, this is what we are going to be calling the original height of the swimming pool. Maybe in case I consider it to be my swimming pool. So the distance from this point up to this point is what I'm going to call the real depth of the swimming pool. However, when you use your eye and you look at this pencil that has been immersed in water, it's going to appear shallow. Why? Because of refraction of light. Now, the distance from where you are seeing the pencil up to the top is what we call the apparent. We call it the apparent depth. This first one is called the real depth. Then the next one, from the pencil up to the top, is what we call the apparent depth. Then the distance from this point up to here down is what we call the apparent displacement. So that one, we call it apparent displacement. So these are the three words we are going to be using in this lesson. What we call the real depth. So real depth is the distance from where this object is up to the top. Then the distance from where the object is up to the top, the image up to the top, is what we call the apparent depth. Then from the original object up to where the image has stopped is what we call the apparent displacement. The further the particle has been taken from its original point to the other point is what we call the apparent displacement. So when we talk about displacement, we are looking at the change in the distance, the change in which the distance, the way the distance changes from one point to another. So that's what we call the apparent displacement. Now, let me test you. You're going to type for me in the chat, and you tell me, this is my ruler. Oh, let me draw another one, a better one. This is my piece of ruler. And when I insert it, it appears here. This is 15, and the distance from here up to here is 10, is 5. Now in the chat, who can tell us? Can you type in the chat what is our real depth, what is the apparent depth, and what is the apparent displacement? You type in the chat and you tell us what is the real depth, what is the apparent depth, and what is the apparent displacement. Which values will you give the answer? I'm waiting for the answer. You can type in the chat. If you wish, you can raise up your hand as well. It can work. You can use any of those two options. You can raise up the hand. You can type in the chat, or you can tell us what is the real. I want the distance for the real depth, the apparent displacement, and then the apparent depth. What could be your answers? Bashir's daughter? Bashir's daughter is saying the real depth is 15. Thank you. That is correct. Joy. I'm seeing Joy. I'm seeing Jacqueline. What about now the apparent displacement? What is that apparent displacement? Apparent depth is 10. Thank you, Bashir. Bashir, can you unmute? Okay, kindly tell us.
The apparent displacement is 10. Okay, no. The apparent depth is 10. Then the apparent displacement is 5. Then the real depth is 15.
Okay, thank you. Thank you so much. So we have said that this was the original point, and this is where your image has been. Now, the distance from the original point to this is what we call a displacement. It has been displaced. It has been moved, is what. So here, your apparent displacement is this 5. Then the distance from the top, from one medium to where the object is what we call the real depth. And then this other distance from where your image is up to the top, where you're going to view it, is what you call the apparent depth. So those are the words we are going to be using in this session. So you need to know each of the meaning of each of those words, such that you can be able to understand. Now, we are going to look at real and apparent depth, and we are going to ask ourselves, how are they related? How is real and apparent depth related? Now, we are going to use our glass block. So you have seen these things happening. When you look at a pond, it always appears shallower than it actually is. When you insert or immerse a pencil, ruler, pen, calculator, and other materials in water, they always appear to be bent. When you look at objects, let me say a pin, they will always appear to be nearer. So all those ones are manifestations of refraction. And how are they related? So how are we, here we are going to relate how is the refractive index related to the thickness T? How are they related? We are going to derive how is real depth and apparent depth related in line with the refractive index. So what are we going to do? Now, in case I have this as my glass block, we know very well that in case this is my glass block, you know very well that when you look through a glass block, when I place, let me say, an object at the bottom of the glass block, this object, light will pass through the glass block and then it goes into air. So light will move like this. And then you, a person seeing the object will appear as if it is very close to the surface. So this way you're going to be with your eye. However, when you look at the object, it will always appear that as if it is very, very close to you. Now, what will happen is that, allow me to draw this as my norm. What will happen that for you, you're going to be viewing the object as if the object is at that point. So this object O is going to appear as if it is at this point. Now, what does it mean? So it will appear as if it is at this point. Now, this angle this angle is always what we call the angle of incidence. Now, what I want you now to take note is that if this angle is I, this angle here is also going to be I, and those are what we call alternating angles. Then the angle at which the ray of light moves or emerges out of a surface is what we call the angle of refraction. But I want you to go back now to your math. When we are learning math, we say that if we have two parallel lines, and maybe you have an angle here and the angle you have here, these two angles are always the same. And that's what we call corresponding angles. So that means that if this angle is R, this angle at this point is also going to be R. Then allow me to call this point A, to call this point here B, and I will come and I say, so that is A, B, O, and maybe I can call this one I. The reason why I'm calling it I is because I want to represent that it represents an image, that O, the object, has been moved to I. So this is how my sketch is going to be. So this glass block is in what? In air. Then this distance from the top of the glass block to this point is what we call the thickness of the glass block. And for this particular one, we are defining our thickness as T. That is T. Then I told that the distance from where the object is up to where the image has been displaced. That's what we call the apparent displacement. And when I'm representing an apparent displacement, since I'm talking about displacement, allow me to use the letter D, such that it is easy for you to know that that is displacement. Members, let me know whether we are on the same page. You can type in the chat, yes, we can continue. I want to know whether we are on the same page. Are we on the same page? Okay. Yes. Okay. Now we are going to continue. Now, when we continue, what are we going to do? We are deriving to show how is the refractive index related to real depth and how is it related to apparent depth. Now, I want you to tell me, when you look here, I want you to tell me, what does AO, the distance AO, how do we call it? The distance from A to O, which special name do we give it? What about the distance A to I? The distance from here up to here, how shall we call it? What about the OI, OIO? How do we call it? Yes, now I have seen a hand up. Yes, Shakul.
Master, I'm not I'm not the same page with you. I beg of your pardon, please.
Where?
From where you have said, from the apparent depth.
Apparent depth. Now, like
Yes.
apparent depth is like the appearance. Eh? Appearance. Like when you look, you know swimming pool, eh? When you look into the swimming pool like this, it's going to appear as if it is very close. Now, the distance from the top of the swimming pool to where it is appearing to be very shallow is what you call the apparent depth. But the real depth, imagine there is no water. That's what we call the real depth of a swimming pool. Then the distance from where the object is up to where the image is what we call the apparent displacement. So real depth means the original one. Apparent depth means the imaginary one, that part which you imagine. And then the displacement is the real minus the apparent depth. So here, our A to O is going to be what we call the real depth. That's what we call the real depth, the actual one. Then A to I is what we call the apparent depth. Then I to O is what we call the apparent displacement. In some books, you'll find them using apparent. In some books, you can find them using vertical displacement. Hope we're a bit now on the same page. Now, the person who is observing, who is looking into the glass, always the image will appear to be very, very close. And therefore, now at this point, you notice that we have two surfaces. This is the glass surface, and this is air. And we said that whenever you have two surfaces, light moving from one medium to another of different optical densities, then it means that we are going to apply what we call our Snell's law. And what does the Snell's law tell us? The Snell's law tells us that, okay, now I can start from the Snell's law. From the Snell's law. So from Snell's law, we say that n sine I is always equal to a constant. Aha, very good. Now we are going to apply. At this point, now you are going to follow. Let me write from here. So at point B, our light is moving from glass and it's going into air. So we say that that is n of glass sine of I is equal to n of air sine of R. So here you get n G sine of I is equal to n air is 1. You end up with sine R. Now, after obtaining that one, it means that your refractive index of the glass material is equivalent to having sine R out of sine of I when you divide through. Now, what does it mean? Members, are we together on that? Are we together? I don't want to okay, let me hope. Okay, looking in the chat, people are saying we are together. Now, after obtaining that, we are going to go back and ask ourselves, what can we now do? We have got our refractive index sin I and sin R. So I'm going to come here and ask myself, how can I obtain my sin R? How can I obtain my sin of I? Now you're going to come here. I want you to check out this triangle AIB. Triangle AIB. So triangle AIB is in this form. So this is I, this is A, and this is B. You can note that this is R, and the distance from here, this is AB, and then this is BI. And now you ask yourself, how can we obtain sine of R? Members, from the, how do we get sine R? How do we get sine R? Yes, Chelsea or Joy? How do we get sine R? Or how is sine R given? Chelsea? Daphne, Joy? Okay. Yes, Shakul.
Sin R is given to opposite of hypotenuse.
Very good. For this case, what is our opposite?
Sorry, opposite is AB.
AB. Hypotenuse is?
Then the hypotenuse is BI.
Is BI.
I.
Very good. You keep on. Now, we have another one. We have another one. I want you to extract. Now I want I. A or B? Yes? A or B. Extract. When you extract it, you'll have something like this, and something like this. So this is A, this is B, and this is O. You have here your I. So members, how do we get sine of I? How do we get sine of I? Other people, I'm saying Shakul is back. Okay. Yes, Mayanja Abdullah. Abdullah. Okay.
Sine of I, we can use opposite of hypotenuse, but the opposite to that one, it is AB.
AB,
And our hypotenuse is BO, the longest side.
Is BO. Good. But when you go back, when we go back, we are going to notice that now our N is going to be sine of R out of sine of I. So when we substitute sine R, we got our answer as AB out of BI, and we are dividing with sine of I, which is AB out of BO. So this will give us AB out of BI times the BO out of AB. So you notice that AB and AB are cancelling. So what do we remain? Oh, I didn't create a slide. Okay, allow me to create one more slide. So what are you going to get? So we have noticed that now our N, oh, sorry. Okay. Our N, we have obtained our answer is going to be AB out of I of B times OB out of AB. You notice that this and this will cancel. So N is equal to OB out of I of B. So now that is our N. But we ask ourselves, what does OB represent and what does IB represent? When we go back to our diagram, you notice that OB is this distance and IB is this distance. Now, I want you to know that whenever the angles are very small for approximation, whenever B tries to approach A, what does it mean? That O to B is approximately equal to OA, and IB is approximately equal to AI. Hope that is okay. Now, O to B is approximately equal to AO, so I'll go back and say that O to B is approximately equal, O to B is approximately equal to OA. And then I will say that I to B is approximately I to B is approximately equal to I of A. So now I substitute and I've said that my N of B is O to A out of IB, and IB is given by IA. So when you go back to your diagram, you're going to notice that O to A is the real depth. Then I to A is the apparent. So now I'll come back here and I say that my O to A represents what we call my real depth. And I to A represents what we call the apparent depth. Are we together, dear friends? Let me know whether we are together up to that point. Okay, according to, are we together up to that point? Okay, good. I don't know whether there are people who are writing, but I can go back such that people can summarize. Are people writing, or we can continue? Let me know in the chat. You just say writing, we continue. Writing. Okay, we'll give Joy some few minutes to proceed. So they can ask you, how can they set? They can ask you to show that a refractive index is equal to real depth out of apparent depth. So that's how you derive it. Okay. Okay, we can continue. Joy, take a screenshot. Okay. Now, what is the other relation we need to know? The other relation is the one between refractive index, the real depth, and then what we call the apparent displacement. And how are they related? And how are they related? So that is what we are going to look at. So I'm going to ask, I first draw a simple sketch. So that is my simple sketch, because we have said that consider an object O placed at the bottom of a glass block. So this is an object O that has been placed. So this is going to be our real depth. And now like this is what we call the thickness. So the real depth is what we are representing with T. Then I have told you already that this distance up to where the object is, this is where we have our image. So this distance here is what we are calling the apparent displacement, and we shall call it our D. Then we shall go on and call this one our A. We shall call here our B, and then like that. So you know that this is the angle of incidence, which is I, and we have said it is given to this one, which is also I. Then the angle that gets out is what we call the angle of refraction. And we know that this angle is going to be parallel, they are going to be corresponding with that one. So when they talk about A to I is what we call the apparent depth. When you talk about I to O, we call the apparent displacement. Then from the top, B to O, or B, like this vertical one, is what we call the real depth. So now those are some of the things that we have. And it's the one now we are going to use in order for us to be able to derive. Whenever you are doing light experiments, don't forget to put the directions, which are the angles. But still here, I want you to know that the Snell's law is going to be applicable for whatever step we take. So when I'm at B here, I'll say that at B, applying Snell's law, so we shall say that our light is moving from glass and is sine I is equal to N sine of R, whereby N, this N here is this medium where light is going. So if that medium, we consider that light is moving from a glass to air, what does it mean? It means that for this particular one, our N is going to be a 1. So I'll have Ng is equal to sine of R out of sine of I. I don't know whether that is okay. And now this one is going to be called our first equation. Members, let me know whether we are fine up to that point. Are we together up to that point? Okay, we are together. Now, after finishing that, we are going to go back. Where are we going to go back? We are going to go back and ask ourselves, how is refractive index related to thickness? So we have already derived. And what have we said? We have said that when you want your sine of I, we have said sine I from our diagram, sine of I is AB, A to B, so we have said it is, to get our I, we are going to extract this triangle, but I feel we don't need to extract it, but there is no problem. This is where we have our O, this is where we have our A, and this is our B. So this is what we have called I. So to get sine of I, we shall say that sine is given by the opposite out of the hypotenuse. And then in order for us to get the other one of R, we have already seen that this is where we have our R, this is A, and this is B, and this is where we have our I. And we have said that to get sine of R, we shall always have our AB out of our hypotenuse, which is BI. Now, remember from our previous thing, we have obtained that our refractive index, N, or what we call our N, is given by sine of I out of sine of R. So when we substitute from our previous slide here, we said N of glass is sine R out of sine I. So here, this is R and this is I. So our sine R is this. So I will say AB out of BI. This is BI divided by AB out of BO. So this will give us AB out of BI times O to B out of A to B. So you can notice that this and this will cancel. So you remain with OB out of BI. And this is equal to the refractive index of N. Now, we are going to do some kind of analysis. And which kind of analysis are we going to do? We say that O to B is approximately equal to O to A. And we say that I to B or B to I is approximately equal to I of A. So meaning that when we come back here, we shall say that refractive index is equal to O to A out of I of A. Then we ask ourselves, what is the distance O to A? So when you go back here, you notice that O to A here, this distance is equivalent to T, which we call the thickness. So here I'll say this is T out of I to A. Now, in order for you to get I to A, what are we going to do? Since the whole of this one is T and the small one here is 5. So what are we, and this one is B. So what are we going to do? We are going to come back here and say that our I to A is like you have, this is T, and from here up to here is equal to D. Members, can you tell me which distance do you have here? In between here, what distance shall we have? You can type in the chat. We can type in the chat. What distance are we going to write there? Remember, the whole thing is t, and this small one is d. What about this distance remaining? Thank you. T minus d. So here I'll have my t minus d as my refractive index n. So what am I going to do? Now, we are looking for the relationship between the refractive index, the depth, and then our thickness. So now when you reach at this point, you can do the other mathematics of cross multiplying. So you get n, t minus d is equal to t. So what is going to happen? You are going to say nt minus nd is equal to t. So your interest is nd. So I can say that n of t, I bring the t this side, is equal to n of d. So since we are interested in n, it means that I can write it again as nt minus the t. So t being the common, I factor it out. So then here I'll remain with n minus 1, and this side I'll have n to d. So since I want d, it means that I can, have t out of n into n minus 1. So now what is going to happen here, you can even make it much better by entering the n inside. So when you enter n inside, it means you'll have t into n out of n minus 1 out of n. So this will give you t into 1 minus 1 out of n. And this is our d. So that is the relation existing. Hope we have got that. Kindly let's write or summarize quickly. So let's summarize. Okay. I don't know whether people have finished. Have you finished? This is A to O. Then this was I. This was I to O. In case you are finished, you tell me. Okay, I go to the next slide. So they can tell you to derive that kind of relation. Yeah, they can tell you to derive it. Okay. Oh, okay. Now, for small angles in radians, this distance here, O to B, is approximately equal to A to O. Like when the angles are really very small, like the heights or the distances are almost negligible or are almost the same. So in case here there is 5, you'll find that this one is approximately equal to 4.8 whenever these angles are very small. So very small angles will yield almost the same figure or the same distances. So that is the meaning that for this hypotenuse will be approximately equal to the height, which is O to A. Okay, you let me know when you finish and then we start. When you finish, you let me know and then we start. Done, done. Okay, now when they ask you to derive it, kindly you go on. You go on and then you derive it in that way. But I want to let you know that when you are deriving, at least make sure you define what you are using. So you define those different things that you are using when you are making your derivations. Don't just derive out of the blue without people understanding what you are actually doing. So there's a sample question. You can write that sample question somewhere. They can tell you that derive an expression for the apparent displacement of an object when viewed normally through a parallel side glass block. So that's how they can set it for you and they'll ask you to derive. So you write it somewhere and then we continue. Okay. Hope we are finished. So when they tell you, always you start with an opening statement. You can say that consider an object or placed under a glass block of this thickness and the rest of that. Now, one, I want you to take note that whenever you have a composite arrangement for the different media, when we talk about composite means that it's made up of different let me say, different materials. That is the simple meaning. That whenever you have it when it is made up of different materials, you don't need to suffer to get for you to get the total displacement where your object is going to be. Take an example. When you place an object here, and you place here water. After water, you place here glass. After glass here, you place paraffin. Yes, something like that. So all these materials will have different what? Will have different refractive index because water, it is different, glass is different, paraffin is different. So in order for you to get the displacement at which this object has, because they can ask you, what is the displacement, the particle? Then for you to get it, you don't need to you need to just calculate the individual of each, this, and this. And then afterwards, you go on and you obtain the total displacement. So where the total displacement you get, that is where the refractive, that's where that will be the total displacement for that particular particle. So that's how you do it. In case there are very many mediums that they have placed over, then that's how you do. Take an example. That means that in case you have D, it will be D1. In case this is the first one, let me say this side is water. What I do, I will say now, my displacement is going to be T1 into 1 minus 1 out of N1. Plus, I go to 2, I will say T2 into 1 minus 1 out of N of N2. Like that. In case they are 3, then I'll go on and I'll say plus T3 into 1 minus 1 out of N of 3, whereby the 3 is the thickness for that particular material and N is the refractive index of that particular material. That's when the mediums are many. So even if they are 50, for you do it like that. You just keep on adding for each of those individual materials, and then after you get the total. So you can make a simple summary and then we continue. We can now look at one more relation and then we can look at an example. Have you finished, friends? You can let me know in the chat, those who have finished, to write that statement and look at an example. Not yet. Okay, let's write. When you finish, you let me know. Finished. Okay. One person so far has finished. Finished. Okay, done. Okay. We are going to look at an example. We start with this example. They're asking, a swimming pool appears to be only 1.5 meters deep. If the refractive index of water is 4/3, calculate the real depth of the water in the pool. Can we first try it on our own and check ourselves? Let's first check ourselves and see whether we can reason it out and do it. Let's first try. Okay, looking through the chart, people are getting 2 meters. Very good, very good. Okay, now here we shall say that N is equal to real depth out of the apparent depth. That is what we use. So N is the refractive index of the liquid, which is 4/3, is equal to the real depth, which you don't know. Real depth out of the apparent depth, which is 1.5. So you do your cross multiplication, and then you'll come up with your depth as equal to 2 meters. Okay, we can try another one. We are doing another one. So for this one, they have told you that an object O at a depth of 3 meters below the surface of water is observed directly from above. Calculate the apparent displacement of the object if the refractive index of water is 1.33. What do? You can you may sketch or you may not, no problem. So this is our object. And they have told that it is 3 meters below the surface of water. That is the 3 meters. Now they're asking the refractive index below the surface. This is water. This is water. The refractive index of water is given by 1.33. So we have said that to get the apparent displacement is given by the thickness into 1 minus 1 out of n. And now since this is water, we shall say W. So to get the displacement where the particle has been displaced, where you are seeing it, it will be the T, which is the thickness, which is 3 into 1 minus 1 out of 1.33. Then you get your answer. Can everyone first calculate the answer and see what you get? Looking through the chart, Kavashailila is saying 2.233. Another Daphne is saying 99 out of another. Since now the answers are different, so we need to find out why. Now, one, in physics, please never leave points, sorry, never leave your answer in fractions, you always write to at least 4 decimal places. And me, I'm also getting these answers. Clever, Lenovo, they have got Kabashaila. Yes, that answer. Yeah, I'm getting an answer of that nature. So that is the answer we get. And this one, we shall say in meters. Yeah. So when you find yourself getting fraction, please always conclude in decimals. Okay. Hope that is very, very fine. So we are going to continue and try another one. Okay. Now, this is now an example I've told you where we have different slabs. They are telling that a tank contains a slab of glass 8 thick and of refractive index. Above the glass slab is a layer of a liquid of thickness, this is it, and above like that. So I want you to also first try out this number on your own. Using the other idea I've told you. And here, don't forget that you consider the thickness of that particular material alone. We are trying. So first find for the first slab, go find for the second slab, find for the third slab. In simple terms, I can make a simple sketch whereby this is the first slab, a tank. Hope you know tank slab, where the tank sits. That's what we like. That is 8 centimeters. And its refractive index is 1.6. Above this glass, there is a liquid. So this is the liquid. And this thickness is equal to 4.5 centimeters. And a liquid and the refractive index 1.5. This liquid has 1.5. This is a liquid. On top of it, there is another liquid floating at 6 centimeters with a refractive index of 1.33. So the thing is put at the bottom of the tank. Yes. Now, okay. Now let's calculate and find out what is the First, find the apparent displacement. Oh, someone is getting 12.5113. Another one is 0.0599. Okay. Taking out, okay, I'm seeing the answer. Oh, the other one, taking out, we just placed it in the calc. So absolute refractive index literally means something moving. There is air as one of the mediums. That is the refractive index. There is air as one of the mediums. But literally it is the same with the refractive index. Okay, I'm seeing people are getting the answers, though they have not got it. Onwe Kavashalila. Kavashalila, can you take us through? Kavashalila. I don't know that you can unmute.
Well, sir, I first got the apparent displacement for the total.
How did you get it?
I got the individual displacements and I summed them up.
Okay, can you share with us the individual displacements you got for the first material was?
3.
3.
Then the next
Plus
was 1.5.
1.5.
The next was 1.48872.
Okay.
And I got the answer as 5.98872.
Okay, these are
That is,
centimeters.
yes, centimeters. So that's displacement, but they said we find the apparent position O. Yes, so I said that for the real depth, it's just the sum of the thicknesses of the individual layers.
Yes.
So meaning the real depth is 6 plus 4.5 plus 8. Minus 5.98872. Then the answer was 12.511 centimeters. 3.
Okay. Okay. Thank you so much. Yes. Now, members, here, one thing you need to check out is the word. The first one was asking for apparent displacement. This is asking for apparent position. Remember, for apparent position, where the particle or where the object is equivalent to what we call the apparent or what we call the apparent depth. Okay, so here's like they're asking for the apparent depth, apparent position. So you had to subtract. Let me hope, many of you reached up to apparent displacement, but you have not concluded what the apparent position was. Yeah, so what you are, the 5.988 is the apparent displacement. But now they want, that is how far the object was displaced. That's how far from the bottom to where the object is. But now they're asking, what with someone who's above, at what position is he viewing the object? So they wanted you to obtain that apparent position. Hope that is very clear. Let me know in the chat whether we can continue. Are we good to continue? Okay, people are saying we can continue. Okay, now, okay, I'm going to take you back. Now, we are going to look at another relationship. And now this relation we are going to look at how is the real depth related to the angle of incidence, related to the angle of refraction, and what we call the lateral displacement. When they use the word lateral in English or in a simple language, it means sideways. That is the meaning, sideways. So now, when we talk about lateral displacement, whenever light is moving through a glass, through any material, the direction it is taking is not always affected, but it is just displaced through a given distance. So take an example. When you are moving, it is just because you are displaced, because you have a direction that you want to take. But if someone displaces you from that direction, you are going to look out for a way to reach where you are going. So what happens is that initially, when light is moving through any material, it can be displaced through the path initially it wanted to take. So when light is moving, take an example. This is our glass prism. If this is our glass prism, and I have a ray of light that is instant, say this is my ray of light. Since this is the glass has a different refractive index with air, the moment it reaches inside, light is going to get refracted. And once it reaches this surface, since also here there is another material, it will get refracted. But its initial path, light was going to just move straight like this. Had there not been any surface to block it. Now, at the point, this point here, I want you to take note, this point here, from here up to here, the initial direction it was taking, and this distance from where it has emerged out is what you call the displacement, or what you call the lateral displacement, the sideway displacement. That's what we call the displacement. So if this is B and this is C, and maybe here we have A, this is our angle of incidence. And we know very well that when we come inside, this is the angle of refraction. But I want to take you for you to take note that whenever I have something like this, the angle I have here, if this is I, the angle I have here is also going to be R, because two vertically opposite angles are always equal. But when you check very well on our diagram, you are not seeing that. So this is going to be I, two vertically opposite angles. But when you look very well, you are not seeing that part of this angle is being taken up by R. So that means that the remaining angle is going to be the whole of this angle, which is I minus R. Hope that is okay. So allow me to put here that the angle I have here is given by I minus R. Then here, this is my thickness of the glass block. Is that diagram fine? Is the diagram? Bashir's daughter, you got your displacement as 6.022. You are going to check Bashir. Yeah, there is a problem with maybe in your computation, something like that. There's somewhere where you have done a mistake in your computation. There's something you have done wrong in your computation. Check out the calculator and see. You do one by one. Don't insert it at once. Then you see. Okay. Now, when we continue here, you let us know. In case it fails, you let us know. But let us maybe first pay attention here. Now, when you look at my figure here, I'm going to extract a figure that I want you to pay attention to. I'm going to extract a right-angled triangle of this nature, whereby this is D. Here I have I minus R. Here I have my A. This is where I have C, this is where I have B. And now I want to find out what is my sign from there. So if this is sign of I minus R, our sign we said always is equal to the opposite. So here our opposite is the D out of hypotenuse, and our hypotenuse for this case is the longest side on this triangle. Remember when they meet here, this is where we have the 90. So our hypotenuse is going to become our A to B. So what does it mean? It means that my D is the same as having a B sine of I minus R. So after knowing that, what are you going to know? Even here on your day one, don't forget this is the 90. So what are you going to take note of? You are going to ask yourself, what about, I want you now to take note. I'm going to extract another triangle. I want you to take note of this triangle. I have this, sorry. I have this. This is where I have my A, this is where I have my B. And when you look at the glass block here, is the same as T. So I'm completing this, I'm bringing something like this. So when you bring like that, the angle we have here is R. And you are noticing that we have our diagram of this nature. So what will happen is, what is our cos? In case I want cos, I will say that cos of R, cos is given by adjacent. For this time, it will be T out of hypotenuse, which is going to be AB. So it means that my AB is the same as T out of cos of R. You cross multiply, so you'll have AB cos of R is equal to T. What is going to happen is that since I'm interested in getting B, I divide by cos of R, divide by cos of R. So meaning that my AB is equal to T out of cos of R. Now, after obtaining my B, I'm going to just come here in my expression. I remove this AB, so meaning that my displacement D is equal to AB, which is T out of cos of R. Then I'll have sine of I minus R. Now, what is going to happen is that now we can simplify and then write it in a simple way that our D is the same as T. But I know from my trigonometry, whenever I have 1 out of cos of any angle, this is the same as having a sec of R. So where we have 1 out of cos, I'll write here as sec. So I can say this is sec R sine of I minus R. So now this is my relationship existing between the displacement, thickness, and then the angle of incidence and the angle of refraction. Hope we are together on that. In some books, it will depend on the book you are reading. You may find them defining your displacement or lateral displacement as small t, and they can write it as this. So it is okay as long as you have defined what you are using. Sec, sec means, sec means 1 out of cos. That is the meaning of sec is 1 out of cos. When you have cosec, cosec is 1 out of sine. So since here we have 1 out of cos because you have t out of cos. So this is the same as t times 1 out of cos. So this 1 out of cos is the sec. Is the sec. So we can write so whenever they ask you for the lateral displacement, that's how you do it. you finish, you let me know in the chat and then we continue. Okay. Yes, Bashir, let me hope you finally got the answer. Okay, Lucy has finished. Okay, this has finished. Okay, okay. Yes, and when you are making those derivation, in case you feel they're giving you some challenges, always extract those small parts such that you can have your workflow in a logical way. Okay, I think we are going to continue and now look at an example. Okay. And that is the number we are going to try out. Let me draw for you that diagram. That is our question that we are going to try out. Now, okay, make a proper diagram. So they're telling us that array of light is incident onto a glass block of thickness 10 centimeters and refractive index 1.5 as shown in the figure below. Find the lateral displacement of the array BC if the angle of incidence is 60 degrees. So when you look at our formula that we have to use, you are noticing that our D is given by T sine of I minus R sec R. But when you look at the angles being given, we don't have the angle of refraction. Meaning that in order for you to be able to calculate, you need first find the angle of refraction, which is R. Now you come and say that at this point, we shall apply the Snell's law. So you'll say that our light is coming in from the air, sine of I should equal to N into glass, sine of R. So mean that air is 1 times sine of 60 is equal to N glass, which is 1.5 sine of R. So here you'll have sine of 60 is equal to 1.5 sine of R. Then when you continue, you'll ask yourself, what is sine of 60? Then here I can divide by 1.5, divide by 1.5. So I'll end up with sine of R is equal to, so you place your calculator, you'll get 0.57735. Then we know that our R will equal to sine inverse of 0.57735. So when you place the sine inverse of that, you're going to end up with your R is equal to 35.264. But when you are writing your angles, write them to now 1 decimal point. So here I'll say that my R is equal to 35.3 degrees. Now, after obtaining your R, you can come and get your lateral displacement BC. So we can say that our BC is equal to T sine I minus R sec R. But you know that on your calculator, you don't have sec R. So meaning that you're going to write what? Cos. So I'll come here and I say my T is 10 centimeters. So I'll come here and I say this is 10 sine. My I is 60 minus 35.3 times. Instead of writing sec R, I write 1 out of cos of R, which is 35.3. Kindly let's get the answer. Place your calculators and we get the answer. You can place your answer you have got in the chat. Okay, looking through the chat, people are getting 5.12. Okay, so I'll come here and I write that my answer is 5.12. These are centimeters. So that is your B to C. Okay, hope that is very fine. Okay, should we continue? Or some people are still writing? Should we continue? Or people are writing? Okay, you finish? So when you finish, you let me know, and then we continue. Okay, Jesse has finished. Okay, Clever Bithian has finished. Okay. Okay, wait for one more person or two. Okay, Bashiri's daughter has finished. Bashiri's daughter, did you get the other answer? Okay, people have finished. Okay. Okay, let's try out now this one on our own and we see. So we are trying out this number on our own and then Okay, I've started seeing some answer coming in the chat. Okay. Okay. In a few minutes' time, we are going to start. Okay, I think we are going to start. Okay, I've seen some answers coming in. Now, I know there's some people are not getting those answers, but let me hope you have noticed that here, they didn't give us the angle of instance. So that was the first thing you had to do. You had to say your 90 minus 40, which gives you, this is going to be 50. So then after you get the angle of refraction at that point. So what are you going to do? So I expect you to say that from air, they told us that incident from a liquid of refractive index onto a upper side or glass block of refractive index. Now here we are coming from a liquid, sine I is equal to N G of a glass block, sine of R. So I expect that your liquid here, which was 1.33, sine I, which is 50, is equal to glass, which is 1.42, sine of R. So when you place in your calculator 1.33, sine of 50, you will notice that you are going to get your answers 1.01884 is equal to 1.42 sine of R. So I divide by 1.42, divide by 1.42. So you'll say divide by 1.42, we shall end up with our sine of R equaling to 71749. Now, since I'm interested in R, I will say R is equal to sine inverse of 0.71749, and I'll end up with my angle as R as 45.8478, which is approximately 45.8 degrees. Hope we got that. But now, since we are interested in the displacement A to B, I know that this is always my opposite and this is my adjacent. So in order for me to get this, I'm going to ask myself that one I can use. I ask myself, am I using Katoa? Am I using tan? Am I using what? Sine. So which one has the opposite and the adjacent? So you'll notice that that is tan. So I'll come here and I say that now my tan of the angle, which is 45.8, is equal to opposite, which is AB, out of the adjacent, which is 1.8. So when you cross multiply, you'll have your AB as 1.8 tan of 45.8. So when you get tan of that times 1.8, so you'll get your answer of AB as 1.854 centimeters. And when you look at the chart, that is the answer people are getting. So those people who didn't get that answer, probably you used 40 instead of 50. Then when it comes to the lateral displacement, that one we have said that you are going to you can just put it in your formula. Alternatively, you can, yeah. So here you say that my BC will equal to my lateral displacement, which is BC. I know I'm going to have my sine of I minus R. Then I'll have T sec of R. So my thickness is 1.8. Sine of my angle, which is now our I, is 50 minus 45.8. Then here we said we say 1 out of cos of 45.8. So let me place in my calc, and I also confirm that the answer you have is also okay. Times sine of 50 minus 45.8 times 1.8. Okay, which answer did you have? 0.189. So here I have 0.18909. So that is our BC, and these are centimeters. Okay, thank you. I'm saying that at least many of us have the answers correct. So that's how we were supposed to do that particular number. Okay, let me hope we are fine with that. Okay. In case we are leaving you behind, you can alert us. You can alert us. Okay. Now allow me keep okay. Allow me now to give you another one that we can try out and we see. So this is just a test question to test ourselves. So it is going to say, a glass tank of thickness 2T is half filled with a liquid of refractive index N1, and the remaining half is filled with another liquid of refractive index N2. Show that the apparent position of a scratch made at the bottom of the tank when viewed directly from above is given by T into 1 out of N1 plus 1 out of N2. Okay, now this is a proof number. So may I ask you now to first try it out and we see. Try and then we see. In case it has come out, you can raise up the hand and you take us through. In case it has come out, raise up your hand and you take us through. Okay, hope we are trying. Oh, it is failing. Has it failed? Bashiri's daughter, Calvin, BV, Clever BV on Erica. I'm saying Itel, Kabashalila, Lucy, Mary, Naseko, Dion, Abdallah, Mary Dion, Peter Chibelo, Trexie. Is it failing? Okay, you're still trying. Okay, let's try. Let's try. Mary, are you trying?
No, sir, I'm not trying.
Why? Mary? Mary, why?
Sir, I have no idea because I've just joined you just of recent.
Oh, okay. Okay, okay. Now we are going to do it together and we see. Now the first thing always we do, let me ask Kabashalila. Kabashalila. I don't know. Kabashalila, has it failed?
Sir,
Mm-hmm.
I've tried to prove it.
Has it come out?
Yes.
Okay, you take us through.
I first said that I first summarized saying that the thickness is 2T.
Mm-hmm.
Then the thickness of the first liquid is 2T over 2,
Okay,
which
good.
is, then the
Mm-hmm.
thickness of the second liquid is also a half, which is T.
Mm-hmm.
Yes. Then from
Okay.
there, I said that the displacement for all is T into 1 minus 1 over N1 plus
Mm-hmm.
T into 1 minus 1 over N2.
Mm.
Then from there, I tried simplifying and I
Mm.
ended up with the D as
Mm.
being T into 2 N1 N2 minus N1 minus N2 over N1 minus N1
Mm.
times N2. So that is the D, but I'd asked for the apparent position. So I'd
Mm.
said that since the thickness of the glass tank is 2T, then it means the apparent position is 2T minus the other answer I got. So
Mm.
when I simplify, I end up with N1 plus N2 over N1, N2, but that is just the same as 1 over N1 plus 1 over N2.
Okay, thank you. Thank you. That is correct. Okay, so that's how you had to do it, because they told that a glass, the thickness is 2T, is half filled with the liquid. Now, half filled is like, I've filled a half of it. Now, the distance from here up to here is T, and here up to here is also T, because it is half filled. So that means that's where you have the liquid, and the other part will remain. And the refractive index here is N1. For this one is going to be N2. Show that now we say that the displacement D for the combined one is going to be T into 1 minus 1 out of N1. That is for the first liquid, because its thickness is T, plus for the second one, which is T into 1 out of N2. Now, what are you going to notice? You are noticing that T, and when you open brackets, you'll have T minus T out of N1 plus T minus T out of N2. So what will happen that T plus T is 2T. So I'll have 2T minus T out of N1 minus T out of N2. So this is the apparent position, the apparent displacement. So to get the apparent position, or to show the apparent position, we say that for it, you'll always get the thickness, or what you call the real depth, minus the apparent displacement. So the real depth is 2T minus, now the whole of this one, which is 2T minus T out of N1 minus T out of N of 2. So when you open brackets, you have 2T minus 2T. Now, minus and a minus will give you a plus T out of N1. A minus and a minus will give you a plus T out of N2. Now, what are you noticing? 2T minus 2T is equal to 0. So meaning that we shall have T out of N1 plus T out of N2. And since T is common, I'll factorize it out, and I remain with 1 out of N1 plus 1 out of N2. So that's how you get that answer. So that is the approach you can use to get. We say that whenever they combine, for you do not think it is really very hard, for you just get a way of simplifying and making it much easier to you. So now I'm going to give you some few questions that you are going to search about, and maybe you will share your findings. I think we are almost there to our time, but maybe I can give you another one. We can try as well. No problem. So another one I'm going to give you, assuming my assumption is people have done some trigonometry. That is going to be my assumption, that at least many of you have done what? Some trigonometry. In case you have not done, yeah, but let me assume you have done some trigonometry. So it is going to say, this is the number that we have. I'm going to give you two numbers you are going to try out, but all of them are for proving. Monochromatic light is incident on a glass block of transparent material placed in vacuum. The light is refracted through an angle. Light is refracted through an angle theta. If the block has a refractive index n and is of thickness T, show that light takes time T is equal to NT sec theta out of C to emerge out of glass, given that C is the speed of light in vacuum. That is the first one you're going to try out. The second one, now here, make sure you draw a sketch. It will be able to guide you well. It will be able to guide you well. But the one thing you shouldn't forget that N is equal to C out of V. That one is going to be very crucial. Then another one you can try out is going to be light consisting of two colors is incident from air on a glass block of index N. The speeds of ray 1 and ray 2 in glass are V1 and V2 respectively. Show that the distance PQ is given by PQ is equal to TC inverse sine I into V2 out of cos T2 minus V1 out of cos, this is R, R2, R1, where C is the velocity of light in air. So have your block drawn. This is your I. Then this is Q, and you have here P. The whole of this is R2. Then this is R1. Yeah, this is the first ray. This is the second one. Yeah, this is O. This is N. And this is thickness T. So you'll try them in your free time. And see, in case they come out, so much the better. In case they are failing, they require some good trigonometry anyway. They require to have done some trigonometry. But in case you have not yet reached there, at that point of trigonometry, it is well. It is well. You can leave them and then you do them as time goes on. So next time, God willing, if we meet, we shall be looking at critical angles, and then we shall look at those calculations concerning critical angle, and then we shall look at the fiber and the rest of that. So that's what we shall be looking at when we meet again. God willing. Okay, yeah. Okay. So hope you are finished to write. And then I'll request you on the days where you see senior physics, and times in case you are free,